Hi there, this is Further Mechanics Circular Motion Lesson 3 for A-Level Physics. So first of all, centripetal acceleration. So an object moving along a circular path is continually changing in direction. This means that even if it is travelling at a constant speed v, it is also continually changing its velocity. And if you're changing your velocity over a period of time, you must also be undergoing an acceleration. And the acceleration is directed towards the centre of the circular path, and it's centripetal. Or if you're in the US, I've heard people say centripetal. So centripetal or centripetal are the same, one and the same. So first of all, I need to give you an equation for this one. So acceleration is equal to, and it's v squared linear speed squared divided by the radius. So that's the equation for the centripetal acceleration. So acceleration is obviously measured in meters per second squared, velocity in meters per second, and the radius would be in meters. Remember to pause and take some notes at any time. I'm just going to move on. So from last lesson, we've got the relationship between linear velocity and angular speed. It's v equals r omega. And we've also got the equation that I've just given as acceleration is v squared over r. And if we combine these, so we'd have acceleration equals r squared omega squared divided by r. That gives us acceleration is equal to r omega squared, which is utilised quite a lot in question problems or exam questions. And then another one which is more rarely used, because r omega is actually v, we can say that acceleration is also equal to v omega. So there's three equations there. I'll just write the other one just so we get them all in the same place. And you can write these down if you wish. And then what we're going to do is to apply them. So let's move on. So first of all, I've got this table for you to complete. So if you want to pause and have a go, please remember to be very careful with these ones, just like we did in the last lesson, in lesson 2, and convert that properly. So pause, have a go, and then I'll give you the answers. So the first one, angular speed, you should get 4 radians per second. The centripetal acceleration, 32 meters per second squared. Linear speed, 1 meters per second. Centripetal acceleration, v squared over r. Be 2 meters per second squared. The next one, 3 meters on the radius, 243 meters per second squared on the centripetal acceleration. Next one, 1.5 radians per second and a radius of 4 meters. This last one, so the 33 and a third, so you have to do 33 and a third divided by 60, and then times it by 2 pi, because omega is 2 pi f. So 33 and a third divided by 60 will give you the frequency, times by 2 pi will give you 3.49 0.658,504. You should use the full number, radians per second. And then what you'll need to do to get the linear speed is use the equation acceleration is v omega, because we already know the acceleration and we now know the angular speed. So that will give you a velocity of, if you divide them, 0.52 meters per second, and then consequently give you a radius of 0.15 meters. Hopefully that went okay. Let's move on. So, let's have a go at this one. Just pause it, and then I'll take you through it. So, for the International Space Station in orbit around the Earth, the ISS, calculate the centripetal acceleration and the linear speed. Data that's given, it completes 15.5 orbits of the Earth every day. as it has an orbital height of 400 kilometers, and the Earth's radius is 6.37 times 10 to the 6 meters. So first of all, let's have a look. Now you could actually, do B first, then A, or you can do A then B. It's completely up to you. Doing B then A might be the quickest way. So let's have a look. So the first thing that we need to do with anyway is that it completes 15.5 orbits per day. So in a day there is 86,400 seconds. So let's divide that by 15.5 orbits. And that will tell us how many seconds it takes to go around the Earth once. So if we do that, we get 5,574.2 seconds per orbit. So using that, you could find out the angular speed by doing 2 pi over t. Then do the centripetal acceleration, A equals r omega squared. But then we have to find the linear speed anyway. So we could find the linear speed first, so that would be v equals 2 pi r over t. So 2 pi r, so 2 pi times the radius. Now the radius is the 6.37 times 10 to the 6 plus the 400 kilometers. So plus 400 times 10 to the 3. And then divide that by the time period of 5574.2. And that will give us the linear velocity, which is 7,631 meters per second. Or 7.63 kilometers per second, however you want to display it. But that's the linear speed. And now we've got the linear speed, it's very simple and straightforward to get the centripetal acceleration. So I'm just going to make some room here. So make sure you've got the 7631 written down. And let's do the acceleration. So the acceleration is v squared over r. So we just need to square the velocity that we just got. So 7631 squared divided by the radius. So the radius of orbit is simply the 6.37 times 10 to the 6 plus the 400 kilometers, 400 times 10 to the 3. And if we put that on our calculator, that will give us an acceleration of 8.6 meters per second squared, which makes sense. Surface gravity is 9.81 meters per second squared, and as we move out, by the time you get to the International Space Station, 8.6 is is definitely correct and feasible. So let's move on. It's quite a tricky one, this. If you want to pause and have a go. A particle travels at a constant speed around a circle of radius r with centripetal acceleration a. What is the time taken for 10 complete rotations? And what I want you to do is to try to derive an expression for t in terms of r and a. And after you've done, I'll take you through the solution. So we've got two equations. We've got the acceleration, which is v squared over r. And we've also got the straight line velocity, which is 2 pi r over t. Now, if you didn't have a clue and you want to use this as a starting point, please feel free to do so. And then I'm going to carry on. So what I'm going to do is to substitute the v equals 2 pi over t into the acceleration equation. And I'm going to write AR equals v squared. So I'm just going to take that r up there. So that's AR is v squared. And then I'm going to square this v. So I end up with 4 pi squared r squared over t squared. And we want our expression for t. So I'm going to take the t squared up. So t squared is equal to 4 pi squared. Now it would be r squared, but that r squared and r will cancel out. So I'm just left with 4 pi squared r divided by the acceleration. So now we just need to square root for t and then multiply for 10 complete rotations. So therefore t will be equal to, square root of 4 is 2, pi squared, square root will be pi, and then we've got root r over root a. Root r over root a. And then, as I said, we need to do it for 10 complete rotations. So the final answer will be the time period is equal to, we need to times by 10, so 20 pi root r over a. Pretty challenging. Hopefully that went okay. Let's do one more. So a particle of mass m moves in a circle of radius r at a uniform speed with frequency f. What is the kinetic energy of the particle? And I want you to derive an expression for the kinetic energy in terms of its mass, radius, and the frequency. So I'll take through the answer in a second. So we've got the kinetic energy, which is a half mv squared. And we've got the velocity of an object exhibiting circular motion, travelling in a circle, to take into account frequency, as v equals 2 pi rf. So we just need to square the v and substitute it into the kinetic energy. So the kinetic energy will be a half times the mass times, we've got 2 squared, which is 4, times pi squared, times r squared, times f squared. So half times 4 is 2. So the answer for the kinetic energy will be 2 times the mass, times pi squared, times r squared, times f squared. And in the question, it wanted mass, radius, and frequency. And in our answer, we've got mass, radius, and frequency. Hopefully that went okay. Thanks for watching. I'll see you soon.